You're watching DSP Leaders on TelecomTV. This special series of programs is focused on AI in telecoms and is produced in partnership with the ITP. AI is not just about technology. There are a number of important moral issues associated with it. For example, can the decisions an AI system makes be explained? And what about responsibility and how AI deals with bad data? Joining me now to talk us through this complex area is Detlef Nauck, who is Head of AI and Data Science Research at BT. Detlef, thanks for joining us.
Hi Guy, nice to see you.
Now, explaining or interpreting AI systems sounds equally complex and fascinating. Tell us more about we can hold AI to account and make better use of this powerful technology.
Right, thanks Guy. So, as you might be aware, AI solutions are now pretty much ubiquitous. You have them in your pocket, in your smartphone. And here are just two examples of what you are using today. And on the left picture, you can see pictures with ice cream in it, and they're actually from my phone. And I've asked my phone to show me pictures with ice cream. And although I haven't labeled these pictures, the phone managed to find them. And that not only tells you that apparently I like ice cream, but that there's a capability built in that can recognize objects in pictures automatically without you doing. And you have something similar on language processing, so you know that you can talk to your phone, may it be Siri or Google Assistant, or at home you might have an Alexa. And you can converse with these kind of applications and they can answer back. It doesn't always work out, as you can see in this particular picture here. And this is because these systems don't really understand what they're doing. They're doing basically pattern recognition. And the systems that are doing these in images and natural language processing are these kind of deep neural networks. And there's a picture here that shows how that is done with images. So these networks look at areas in the image and these areas overlap. And then there's some internal process happening, and that in the end matches some output. And the system says, I think it's a picture of a bird, a dog, a cat, a boat, or some ice cream. And these systems are growing more and more. So the number of adjustable parameters in these systems are now in the millions or even billions, depending on where you look. And so here, this chart shows the growth in the number of parameters. Each parameter is a number, and you have to adjust this number so that the overall performance of the system becomes better. And this is not only very tricky and complex computation, but it also requires a lot of effort in computing. So you can see that for one of the larger ones, the natural language system called BERT that Google built, it takes about $4,000 to $12,000 in terms of compute cost in cloud compute to train the system, and it uses the carbon equivalent of a flight from New York to San Francisco whilst it's doing this. So building these kind of massive systems is not really sustainable except for very specific exceptional applications. And the question is then, when you build something that big, how do you know that it does perform to a standard and does what you want it to do? And we have seen a lot of examples in AI where things have gone wrong in the way AI has worked with data. So here's an example from a system that Amazon has used to scan CVs, and it was shown that it is biased against women. And you may know that facial image recognition is very much a problem, and it's racially biased, gender biased. And this is because we can't really see into these systems and see how they have been built and understand that this sort of bias is built into the systems. So we only discover it through application, and then we know, okay, something went wrong, but how did it go wrong, and how can we be sure that a future system is built to better standards? Another example here is from medical imaging. So AI is very often claimed to be much better in interpreting things like X-rays or MRIs. But very often you find that this is not the case because the AI has used information in the picture that is not obvious to a human observer, but that can be detected by the AI, and it cheats its way to the result. So here's an example of images from lungs, and the system has actually picked up where the image was taken, at which hospital, or by which system. And because the people with an illness were basically looked at different hospitals, you had a chance of predicting who has a particular illness based on that information alone. So the system has not really learned to understand X-ray images. And you can't tell that this is the case until you test it and sometimes by accident find out that it's doing something like this. There's also a lot of discussion around how do we make sure that algorithms that make decisions on our behalf can be held to account. So how do we make sure that the decision can be challenged, that the decision can be explained to somebody, that maybe it stands up in court? All of these kind of questions are being asked. And just recently, the Information Commissioner's Office, the ICO, has released an AI auditing guideline, which is very strong on explanation. So they think that somebody who uses complex AI systems should be able to explain what they're doing and how they compute their outputs. Another reason to understand better what AI systems are doing is that they're very often part of very complex systems and complex software code. Here's an example of an article from The Guardian where they write about this accident that the autonomous Uber car had, which ran over a person that went across the road. And it turned out that the image system had detected an obstacle, but some other system that was controlling the brakes decided not to brake. And so you might have competing AI systems in one larger system that make different decisions, and then you really need to understand how that works together and what the overall outcome or the overall decision might be. And you need to be able to not only potentially explain this, but you also need to be able to learn from it when things are not working as intended. And the more complex these systems become, the more difficult this is. And when we look into science, then one of the core principles is called Occams Razor. And this is the idea that you prefer a simpler model when you have the choice between two models. And this is because a simpler model is more testable. It's much easier to figure out what it's doing. A more complex model is more difficult to test. It has more degrees of freedom. And when you test it, you might basically forget to try out a certain type of the input space or the certain area of the input space that could lead to certain outcomes. And therefore, it's always a good idea if you have the choice between two models which are equally good, go for the simpler one. That doesn't always work. So sometimes there is the need to have a complex system. Right? So if you want to fly to the moon, you need a complex spaceship. You can't do it with a glider. But we will still always want to understand how does the system work. So if you have a complex plane, then you want to be sure that it has been built based on physical understanding using the best engineering methods. And you don't want to be told this is a magic flying machine and you can trust it. So how do we do this? How do we go about this? And why do we want explanations out of AI systems? And in the first instance, we want to know that good science has been used to build them so that we can trust them and that we find causality in the inputs and the outputs, that it's not just mere guesswork. And we want to make sure that the features and variables that are used to make decisions actually have something to do with the domain and the output and are not just random, like in this example where the medical imaging system was cheating and using information that has nothing to do with the patient to make a diagnosis. We want to know that the systems have been used ethically or been built ethically, and that they make fair decisions, that they're not biased against groups of people, for example. And we want to be sure that this is the case, and we want to basically see this in the system. We want to challenge the outcome of decisions. So if you apply for a loan and the bank says, no, you can't have it, you would like to understand why this negative decision has been made. Maybe you want to challenge it. And you can only do this if you get an explanation that is somehow related to the financial domain in which this decision is made, so you can argue against it. We may have to follow legal and regulatory obligations. So in GDPR, for example, you have the right to an explanation if the decision that is made by an algorithm has a significant impact on you. And that means as somebody who builds a system like this and wants to use it, then you have to make sure you can actually generate explanations just from the legal standpoint. And obviously, we want to learn from mistakes and accidents. So if something goes wrong with an AI system, you want to be in a position to basically forensically analyze why did this go wrong and how do we make sure it doesn't go wrong again. And we can learn from areas like aviation, for example. The airline industry is anything that goes wrong is analyzed to the nth degree to make sure that the cause is understood and that you can prevent things from going wrong again. So what sort of explanations can we get out of AI systems? Let's just have a look at what's possible. So you can use similarity. So AI systems, the modern AI systems, they basically do pattern recognition. So they perceive an input as a pattern. And then you can say, why do I see a particular output? You could say you see a particular output because what you have used as an input is similar to this other input where we know the output. And so this is here in this example, your input is something small and round, and therefore the answer is the same for all the other small and round objects that the system has seen before. That is explanation based on similarity. You can create rules. So you could have systems that have learned to look at individual input attributes and say, okay, if the size is small and the color is green, this is a P. And it's not a strawberry and not a raspberry. So you get some kind of interpretation from what the system does by the way it has been constructed by using rules. And this is typical for systems like decision trees. And then you can have equations. So you could have a mathematical relationship between attributes, so your size and maybe the color space. And so if your input data is at the top right, then it's green and it's small, while raspberries and strawberries are bigger and more reddish. And therefore you can say, okay, P's are sitting over the line in this equation, in this graph, and the equation for this graph is basically your explanation. And these are principally the three ways of getting explanations out of AI systems. And then you can find these kind of types of explanations in libraries that you can download and use. So here's one that is called Lime. And what this does, it looks at all the input attributes and basically tries to figure out, is the input attribute contributing to the output or distracting from the output. So here's an example for mushrooms, if they're edible or poisonous. And you can see for each of the input attributes, does it contribute to the mushroom being poisonous or to the mushroom being edible? And here you have more evidence that it's poisonous for this example. You can do the same thing for images. So here in the image below, we ask the system, which pixels make you think there's a cat in the picture? And it can highlight these pixels. In this example, it works quite nicely, but I'll show you another one where it doesn't work so well in a minute. Another technology is called SHAP, which is very similar to the Lime concept that you have just seen. So it again looks at the individual attributes, but it now can give individual credit to attributes and tell you something about the strengths by which an input contributes to a certain output. And So you can see here in this particular example, like a small medical example, maybe where the output could be the dosage for some medicine, and the output is made up individually by adding up the numbers in the picture on the right, and which then contributes to the individual attributes, how they contribute to the output. These systems all are based on what's called a local model. So here's an attempt to visualize this. So what you typically have is you have very complex decision boundaries in AI systems. So here this attempt tries to show this with a red or reddish and the bluish area. And one class of output sits in the reddish area and the other class in the blue. And the decision boundary is basically where it switches from red to blue. And you can see this is a very weird shape, and there's no way you could explain in words what this shape looks like. So you can't explain in a kind of linguistic way with words what the system does. So what they try to do is they try to say, okay, if you wanted to explain why the red cross is classed as being red, then what I can do is I can draw this dotted line along the decision boundary in the area where this cross is, and I can say this particular data point is red because it sits to the left of this line. All the blue points in this neighborhood sit to the right. Therefore, it's a red point. So this is the way they try to explain this. This has the disadvantage that it not necessarily works well, because you could have an actual decision boundary which is very weirdly shaped, like this one here, and if you try to approximate it with a line, then you have to make mistakes. So you cut across some complex boundaries, and it might not work so well. And this is one of the main criticisms. If it would work, then you could use the local linear model as your decision-making process. You didn't need the complex one at all. And that's one of the arguments that these things typically can't work. Here's another example of explaining the output of images. So here we are comparing human attention and the kind of attention that an algorithm pays to a picture. So here the question is, what is covering the window in the top row? And humans naturally look at the windows that they detect in the picture. And this is, you can see the human attention focuses on windows. The algorithm that comes up with a correct answer looks all over the place, but it doesn't really look at the windows. You see only very little attention in the right window there, but everything else looks at the bed and the light for some reason. And same thing in the row below, where the question is, what is the man doing? He's playing frisbee, and humans look at the person and they look at the frisbee. And the neural network in this case looks everywhere but at the frisbee. It still comes up with the same decision. So that tells us that these systems don't actually understand anything, and that the input features they use from an image don't really have anything to do with the meaning of a scene. So these sort of explanations are not really explanations at all. Yet another attempt is to use something that's called a counterfactual. And here the idea is that when you get an output from an AI system, let's take the loan application example again. If the system tells you, no, you can't have the loan, then you could say, oh, please show me the closest loan application to my loan application in terms of similarity of the inputs that I've given you, and where this other loan application got approved. And then you can compare your application to the counterfactual, and which is also a valid data point. And you can then compare and see, in this application there was maybe more saving or a higher income, which then led to the positive decision. And so then you would know what you would have to change in order to get a positive outcome. That's the idea here. The disadvantage is that you may not be able to change your input compared to the counterfactual. It's not so easy to get another job and a higher income, for example. And you might get many counterfactuals that are equally similar to what you have used as an input. And then again, it's not really helping. So it's not a bad attempt because it gives you real data and shows you an alternative decision for a very similar data point, but it's not really explaining why your particular input got the decision it got from the system. When we talk about explaining or interpreting AI systems, we also have to think about who's this explanation for. Is it for an expert? So do we have something like a dashboard in an airplane that only pilots can understand? Or are we aiming for something like a dashboard in a car that everybody who knows how to drive a car can understand? So an explanation depends very much on context. Who is the recipient of the explanation and what's the purpose of the explanation? And that is very much an open research problem. How do we craft an explanation out of an AI system in a way that it satisfies the user or whoever requires this particular explanation? And I mentioned this other term, interpretability, or being interpretable. The idea here is that researchers say you shouldn't really try and explain the output of a system. What you should be doing is you should construct a system that you can look into and that you can interpret. So no matter how complex it is, you should be able to see inside, understand the mechanics of the system and say, aha, it creates an output because this is what it's doing internally. And this is the idea of interpretable systems. And if you're interested in this topic, I recommend that you look at the work of Cynthia Rudin. She actually stood up a team that won against a highly complex deep network, which is a black box. And there was a competition where the researchers had to build models and to explain outputs. And what she did is she built a simple model that is interpretable, and therefore you could see why a particular output was created. And she demonstrated that you don't need these kind of very complex black box models. You can build something that is interpretable and you can see into it. So this could be an alternative way of building AI systems and saying, okay, let's try and build them in a way that we can see inside and understand the mechanics of it.
Detlef, thank you very much indeed. Absolutely fascinating. So many questions and thoughts arising from that. One of my immediate takeaways is there seems to be a lack of real understanding by AI systems. Is that the case, and is that a big issue?
Well, the kind of modern AI systems that you're seeing in use and that are seeing reported on in the press are typically deep networks. They are the ones that are being used to do image analysis or natural language processing. And you could argue that in many use cases, you don't need an explanation. But when you get into more complex systems like autonomous cars or decision-making where people are directly affected in some shape or form, and you use the same types of systems, then you get into this kind of area where you say, do I really know what these systems are doing, and do I need to understand this much better? And this is the real challenge. In what sort of application area do I use a black box system because I don't need an explanation, and I just trust the system statistically because I've tested it many, many times, and I know from the way I've tested it that it's 95% okay, and I have some mitigation in place when the system goes wrong, and I keep checking and constantly while it's being used? Or do I build something that maybe is not that perfect and is only maybe 80, 90% correct, but I understand exactly what it is doing, and I can again mitigate in the situation where the model fails and I use something else to make my decision.
And where are we at the moment with the development of these explanation techniques and interpretable models? Are we at a very early stage?
Yeah. So the researchers at an early stage, so there are a lot of methods that claim they can extract explanations from systems, basically either mathematical expressions or rules expressed in the kind of attributes you're putting into the system. But it's very questionable, are these explanations in the sense of the word? So are they explaining to a layperson what the system is doing? There might be explanations for experts who test the system and try to get their head around what the individual inputs are doing. but they're very unlikely to be explanations for a user of a system or somebody who doesn't know what AI is, but is exposed to a decision.
Well, Detlef, we'll come back to you very soon with the Q&A session, and hopefully we'll have many more questions from our audience for us to discuss. And if you haven't already done so, then please do send in your questions to Detlef and all of our speakers today. We'll be hosting the Q&A session here very shortly, in about 5 minutes time or so. So please keep watching and keep your questions coming. But for now, thank you.